The second law of thermodynamics. In this video, we take a look at the concept of the heat engine or simply engine. Just like an electric motor in which you have a device that converts electrical energy into mechanical energy, a heat engine or simply engine is a device that transforms heat into work or mechanical energy. You have a quantity of matter which is regarded as the working substance inside the engine, and the working substance undergoes inflow and outflow of heat, expansion and compression, and sometimes change in phase. For example, in an internal combustion engine, the working substance is a mixture of air and fuel. If you have a steam engine, the working substance is basically the water inside the steam engine. The simplest kind of heat engine is one in which the working substance undergoes a cyclic process. A cyclic process, you will recall, is a process in which the system goes back to its initial state. So, from initial state, the system undergoes a process, and at the end of the process, the system goes back to its initial state. So, the initial state and the final state are the same in a cyclic process, which means the internal energy initial state is just the same as the internal energy in the final state. The change in the internal energy is zero, which means the work done by the system is just equal to the heat added. W is equal to Q. That's not to say, however, that all of the heat Q is transformed into mechanical work W. All heat engines absorb heat QH from a hot reservoir from a high temperature TH. Part of this heat is transformed into into mechanical work. The rest is discarded into a cold reservoir TC. So, system absorbs QH, performs work W, and discards heat QC. Ideally though, all of the QH should be converted into work. But this is impossible. There's always wasted energy. There's always a heat QC that needs to be discarded. The heat engine's thermal efficiency E is given by E is basically the ratio between the work done W and the input heat QH. Thermal efficiency basically tells us, or describes rather, how well a particular heat engine is able to convert QH into mechanical work. E is equal to W over QH. W is equal to Q. Q is equal to QH plus QC. QH is positive, QC is negative. Using Q is equal to QH plus QC, we can convert W over QH into 1 plus QC over QH. Or knowing that QC is negative, QH is positive, this is basically equal to 1 minus the absolute value of QC over QH. E is equal to energy divided by energy. So the unit is cancelled out. E is a unitless quantity, and typically E ranges from 0 to 1. So E is greater than 0 but less than 1. One example of a heat engine is the gasoline engine, or the or what we know as the internal combustion engine. A gasoline engine has a four-stroke cycle. You have the intake stroke, compression stroke, power stroke, and exhaust stroke. You have a piston system. You have a chamber with a movable piston. The piston is pulled down to make room for the air and fuel mixture which is injected into the chamber of our piston system. You have the intake stroke. Next, the piston is pushed up, compressing the air and fuel mixture. So basically, the piston is performing work to compress the air fuel mixture, the system. You have the compression stroke. The air fuel mixture is ignited by, say, the spark plug. The system expands, pushing the piston down. The system performs work on the piston. You have the power stroke. And then the piston is now pushed back, in pushed up, forcing the exhaust, what remains of the ignited air fuel mixture, pushing the exhaust out of the chamber. And then it is pushed back again to make room for more air and fuel mixture, and the process repeats itself. So intake stroke, compression stroke, power stroke, exhaust stroke, and then it goes back to the intake stroke and so on. So one cycle is basically four strokes, when, and then you go back to the beginning of the cycle, the intake stroke. You have a four-stroke cycle. The AutoCycle is an idealized model of the thermodynamic processes that happens in a gasoline engine. For an AutoCycle, the idealized model, for an idealized model of the gasoline engine, the thermal efficiency is given by the following equation. E is equal to 1 minus 1 over R to the gamma minus 1. R is the compression ratio of the engine. It's related to basically the dimension of the piston system and how much the air and fuel mixture is compressed. Typically, the compression ratio typically ranges from 0 to 10. Whereas gamma is the ratio of heat capacities of the working substance or the system. Gamma is equal to Cp divided by Cv. Cp is the molar heat capacity at constant pressure, while Cv is the molar heat capacity at constant volume. The ratio of heat capacity of air is around 1.4. Efficiencies for real gasoline engines are typically around 0.35 or 35%. Of course, as technology progresses more and more, the efficiency of engines increase. So it's not surprising to see, it would not be surprising to see gasoline engines with 40% or even 50% efficiencies, but typically the gasoline engine is around 0.35 or 35% efficiency. The following PV diagram illustrates the Otto cycle. You have intake, air and fuel mixture is taken into the piston system, and then the piston compresses the air fuel mixture, an adiabatic process, and then the air fuel mixture is ignited by the spark plug, which produces our heat intake, Q in or QH. The air fuel mixture, as after it combusts or as it combusts, expands, pushing the piston, so increasing the volume in the chamber of the piston system. Again, an adiabatic process. And then the excess heat QC or Q out is discarded, as well as the exhaust, what remains of the air fuel mixture after combustion. And then the process repeats itself, the cycle repeats itself. More air fuel mixture is taken into the system, into the chamber, it's compressed, ignited, it expands, and then heat is discarded again, the exhaust is discarded, and so on. For a more complete picture of the heat engine, you might want to take a look at the diesel cycle. So you might want to consider that as a reading assignment. So that's it for now. In the next video, we'll take a look at the concept of refrigerators. Thank you for watching.